Good afternoon, ladies and gentlemen, and welcome to the collaborating webinar between the Load Research Chapter and the SAIEE KwaZulu-Natal Centre on Probabilistic Planning for Future Networks. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under both the Load Research Chapter and KwaZulu-Natal Centre playlists. You will find the registration link to the SAIEE TV in the chat box. Please register, it's free. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number from EXA. I'd like to introduce you now to our host this afternoon, Mr. Mondi Soni, who is the chairman of the SAIEE Load Research Chapter. He is also leading few working groups focused on distribution network planning and analysis. Mondi is an elected member of the Council for SAIEE, a voluntary contribution position he has held since 2017. He was awarded the Engineer of the Year in 2019 by SAIEE, the achievement he holds close to his heart. Over to you, Mondi.
Thank you, Mings, and good afternoon to all those in attendance. Good afternoon to the members of the Load Research Chapter. Good afternoon to the rest of the community that is interested in load research as a subject. To introduce the session for today, I just want to go back to history, and I'm going to mention a few dates that I would like you, as the attendee and those who have been following the load research activities, to just have a pen and paper in hand and just take a note of those dates and what we have shared previously, which has been now built up towards what the presenter will be presenting today. To start with, on the 26th of June in 2019, we hosted a seminar at SAIEE House, and the keynote address there was presented by Kat Dedekant. Kat presented a presentation that was titled Load Research Within a Future Planning Landscape. And he mentioned a few aspects that we took as key takeaways. And some of those were, the first one, that the traditional business model is definitely changing and it is going to change. The second one was the distributed energy generation that is taking up. And I think between 2019 and now, there has been a huge change in that space. And the next one was artificial intelligence. And the last was consumer behavioral changes. And that we have seen a lot, especially in the recent past. After that, in 2020, on the 17th of November, Jivan Model presented a presentation which was titled Load Models in Power System Simulation. So in his presentation, Jivan presented load models that were to be used in various types of studies in Power Factory or in Dixieland Power Factory. And he also took us through the typical data that is required for such models to provide accurate results. Then fast forwarding to the recent past, between 2020 and now, there has been a lot of changes that we have seen in the space of load modeling and in the space of power systems, operations and planning as well. So some of those. The first one, we were faced with COVID-19, and at some point we sat around the table and we looked at what could the COVID-19 and the lockdowns, the impact of those, what could those impact be on what we have known as traditional load shapes and the load profiles. We have seen an increase in a number of activities on the customer side, the electricity users. And I think the most important one is we now know that most utilities can no longer afford to have infrastructure that is risk averse, so which is 100% risk averse. Now, with that backdrop, then Jivan today is presenting a probabilistic planning for future networks, and this is a topic that comes in at the time when all the utilities that are involved in the power systems really need to understand what is it that they can do to deal with all the changes that we see in the power system. So the paper that Jivan will be presenting, he will be presenting the concepts of probabilistic load analysis and the applicability of those in the planning and operations of the modern electrical networks. So I understand that Jivan will be using Power Factory as a tool of choice to demonstrate the concepts for today. I think with that introduction, the first thing that I would like to do is to acknowledge the KZN Center. So the KZN Center chair could not make it to this event to do the introduction of the speaker because of some of the challenges that he has. So Richard has requested me to welcome you all on behalf of the KZN Center. And there is information on the chat box in terms of how one can take part in the SAIEE activities for the load research, as well as the KZN Center. The next one that I'm going to do now is to introduce Jivan. Let me just minimize the screen here so that I can see what's on there. Yeah. So Jivan Model is a managing director at Dixal Buesa. I think all those who are in power systems planning and operations that have had to do a study in Power Factory at some point will definitely know Jivan. He holds a master's in electrical engineering from the University of Natal, and he is a registered and practicing professional engineer. He is a senior member of the Institute of Electrical and Electronic Engineers, which is SAIEE. And he is currently, as mentioned, he is the MD of Dixal Buesa. He has over 25 years of experience in the field. Jivan, we would like to hand over to you, sir. Thank you.
Good afternoon, and thank you very much for that warm welcome, Mondi. I would just like to also take this opportunity to thank the SAIEE for this invitation to present this afternoon. I certainly regard it as a privilege, and I really look forward to sharing this information with everyone that's in attendance. So good afternoon to all in attendance, and I really hope you get a lot of value out of this. So for the purposes of this, I'm going to stop my video so that you can maybe see my screen a bit clearer. And I just want to confirm, are you now able to see my screen?
Correct, I can see your screen, Jivan.
Okay, fantastic. And I think what I'm going to do is I'm going to start with the presentation. So as was mentioned before, we're going to look at a concept called probabilistic planning. And the reason why probabilistic planning is going to have to be considered for future networks. So just to give you an overview of what you can expect this afternoon, I'm going to put that slide up there. And the first thing is I'm going to give you a little bit of an introduction. As mentioned already by Mondi, I think there's huge drivers in the industry that are making the acceptance of risk and operating the network and planning the network with some element of risk more and more acceptable, and we have to now start considering this in our plans and operations. So I'm going to discuss why we need to move towards some sort of probabilistic analysis in our network analysis. And then I'll in-depth course on the technicalities behind probabilistic analysis, but to give you some overview, so an appreciation of what it takes to do this analysis. Then I will actually discuss very briefly where it's actually used and the different areas we can use probabilistic analysis. And I would finish off by using two examples where you see the application of probabilistic methods in network planning. One being network planning and the other one in determining hosting capacity of networks. So the aim is so that you can see that these methods can actually be applied going forward. So the current status quo is that most of electrical networks are actually largely managed and operated as passive networks, meaning that there is no active involvement in the network. There may be moving of normally open points and some tap changes, but by large, most of the resources within the network are actually not actively managed. So because of that, you find very deterministic methods are used to plan and operate networks. So for example, you find that if you're doing a plan, you would normally plan to supply the worst case load or the highest predicted load in a network. The issue comes is that the modern network is changing and rapidly. The network itself is changing rapidly. In a sense, you're getting larger penetration of distributed generation. More and more customers are now starting to install storage, and then you also have utility scale storage that's being implemented. Customers are becoming a lot more wiser to the use of energy, and so are starting to implement energy efficiency initiatives. There's lots of talk about increasing electric vehicles into the system. And all of these things are changing the entire dynamics of the actual modern electrical network. So with that, the methods that we're currently using need to be evaluated and see are the current methods for planning and operating the network still applicable in such scenarios. So I've extracted this flow diagram out of the CGRE working group, the C619 work group. They published a very good document in 2014, and they did a sample of many distribution system operators around the world, and they came up with this flow chart that shows how the current planning practice is essentially implemented in the power system. And you will see, I'm going to try and zoom in here so that you have a little bit of a better understanding of that. So by large, normally a load forecast is done, and the maximum demand or maximum expected demand in a network is predicted or calculated. And then deterministic calculations are done. So meaning that the calculations are done to see are there any overloading in the network or are the voltages within acceptable ranges. And then, so are there any constraints that are violated in the system? And if there are constraints that are violated, for example, maybe you have some overloading equipment, some sort of reinforcement is then planned for that network. And then the calculations are run again. And then obviously, once all constraints are acceptable or no constraints are violated, then the plan that was last evaluated for that plan is evaluated, and if it's acceptable, it's then implemented as the actual plan that will go forward into the system. Obviously, if it's not acceptable, then it goes back to looking at alternatives. And then the alternatives are then evaluated, but all of this is done in a very deterministic manner. They determine a load forecast, they determine a maximum demand, and in doing so, they actually then plan how the network should be upgraded. Also, in modern times, embedded generators or within the distribution networks are also taken into account. However, they take into account the so-called worst case scenarios. So what happens is that they would say, let's assume we have a case where we have minimum load in the network and a maximum generation. And the net effect is that they evaluate that as one of the scenarios of how the network could operate. And any plans would be based on that scenario. The fact of the matter is that such scenarios where you have minimum load and maximum generation actually seldomly occur in reality. So the net effect is that any plan that could be derived could actually be an overkill in terms of the plan. And you could end up with stranded assets. And this is fundamentally coming from the fact that deterministic calculations do not take into account uncertainty. Because there's a certain level of uncertainty as to when an occurrence of minimum load and maximum generation will occur. So to illustrate this, the next slide, I think, sums this up, because you find that especially with distributed generation, I think distributed generation is also used interchangeably with distribution energy resources and embedded generation. They themselves, as they are being increased in the networks, introduce uncertainty into networks. Uncertainty is increased because, as mentioned before, customers have their how much they consume. Over and above that, consumers also now install storage, and the ability to control the storage affects the planning and operating of the network as it stands. So just to give you an idea of the uncertainty, what I have here is a very simple graph showing outputs of different types of distributed generation. So there's three types here. There's gas, hydro, and PV. And on the PV, what we've done is we have expanded it to show you different outputs based on summer and winter, and on cloudy and on sunny days. And firstly, you will see between the orange and the yellow curves, that's between summer and winter. Already there's a marked difference in the output of the PV. This is the same PV installation, just the output in winter versus the output in summer. So there's a difference in there. So there's a certain level of uncertainty that's introduced in here. Over and above that, you see that the output that is for a cloudy day, regardless of whether it's summer or winter, is completely uncertain. It's very unpredictable, the output in there. And the reason this uncertainty comes in is because of the fuel source, because PV is a function of irradiation. So cloud cover, for example, will affect the fuel source. Where you can control the fuel source, that may be a bit better. So for example, if you look at a hydro or if you look at the gas, here the fuel source can be controlled, so the output is more predictable, so it's more certain. Where certainly in the cases of PV, it can be regarded as uncertain at certain times. Now, because of the uncertainty, what we want to do is we want to probability, the concept of probability is actually a way to quantify in the system. Now, probabilistic analysis can be applied to any parameter, any input parameter that you may use in your analysis methods. So, for example, consumer behavior. Consumers they're very unpredictable as to how consumers behave nowadays in terms of load consumption. So, because there's uncertainty, probability is a better way to evaluate them. Same with wind. I will show you just now an example of a wind, the uncertainty introduced from wind resources, even solar. This example where I showed you now, where on a cloudy day, the output of a solar plant is completely unpredictable, very uncertain, the output that comes out of it. The other thing to remember is that when you do a probabilistic analysis, your results are no longer singular values. You end up with stochastic results, which require you to use statistics to evaluate the results. But I think you'll get a better appreciation of this later on when I actually show you the examples. So coming back to Seagray's document on planning, the proposed methodology going forward is to look at what they call active distribution networks. And the probabilistic approaches are used to capture the uncertainty in the network itself. Right? So this diagram that you see here on the right, let me see if I can zoom in here a bit. You will see here that this flow diagram speaks about, firstly, customer data modeling. And I think this is tying back to the theme of today's presentation. Part of the load research chapter's work is that how do we model this customer that we can feed it into probabilistic network calculations. And I'm going to be focusing on this yellow block and this green block today. Yeah. But just to give you an idea of how this will work in the future, let's take, for example, a very simple example. We have a line, and we calculate that there's a certain overloading that will occur in this line. Not only will you look at the overloading of that particular line, we also need to consider the probability. How often would that line overload? Okay, and this is where the decision block about unacceptable risk of constraint or violation needs to be considered. Because sometimes, instead of upgrading the line to cater for overloading, you might find that some sort of active management, what you see on the right here, may be a far better way, and certainly far cheaper way, of managing that overloading than actually going for a more deterministic method of saying, let's upgrade the line so that it can cater for this very low probability of overloading that may occur sometime in the future. Yeah. So this layout over here, or this flow diagram, is indicating that in the future, the networks can also be the planning of networks, that active network management or operation of the network also becomes a planning option. Yeah? So you don't only have to upgrade networks, you can actually manage them and operate them in certain ways that it will help solve some of the planning constraints that are identified. Okay, so let's get into what probabilistic analysis is. In order, we talk about the customer data modeling, and this is done by means of distributions. So the fundamental input to any probabilistic analysis is distributions. The definition of a distribution, it's a mathematical function that describes the probability of different possible values of a variable. Okay, so you will get different values that come out, and it defines the probability of that value occurring. Now, you can apply distributions to pretty much anything in the electrical network. You can apply it to your active power, reactive power of your loads and generators, your tap positions, your voltage set points. Even breaker statuses can have a probability. So the probability of a breaker would be either open or closed. And you can define which has a higher probability. The breaker has a higher probability of being open, or it has a higher probability of being closed. Yeah, and this can be defined as a distribution. Now, there are several different types of distributions that are available, and each can be used depending on the use case. So I will show you that just now. But when you define distributions, distributions can be defined in two ways. One is called a probability density function. So it's up at the top right corner here. You'll see you have a density function. Or you can define a distribution as a cumulative distribution function. All right, so that's the diagram on the bottom right over here. So there's just two ways in which distributions can be represented. Yeah. Now, there are various types of distributions that exist. So I don't want to get too bogged down in the details, because different distributions are applicable to different types of use cases. And they give a much better definition depending on the use case that you want to analyze. So to show you this, let's actually look at an example of distributions and how distributions become applicable. So what I have here is a sample of wind speed. So remember, at a site over a period of time. So in this particular case, we have wind speed measured at a specific point for 1 year. And measurements are taken, for example, every hour or every 15 minutes, and it's plotted on this graph here. And I think you can see here that you cannot say with certainty what the average wind speed will be, or what wind speed you can expect from the site. It varies. It varies all the way from 0 all the way to just above 14 meters per second. Yeah? Now, in order to quantify this wind speed so that we can use it in calculation, what is done is a histogram of the wind speed is done. So how this is done is very simple, actually. They define what they call bins. So if you look at the graph over here, you will see at the bottom here, there's different bin sizes. So here's the wind speed bin between 0 and 0.2. There's a wind speed bin between 0.2 and 0.4, and this is in meters per second. Then taking the actual raw data itself, they then sample how many times an occurrence of that particular wind speed in that bin size occurred, and they count it all up. So for example, if you were looking at 4 meters per second, you would run across here and count the number of times you recorded 4 meters per second wind speed. And then based on that, they would add that to the bin. So in total, these bins will then give you a total of the number of times they sampled a specific value. Yeah? So you'll see on the left, it says frequency. And what you will see is when you display this very scattered wind speed on a histogram, you can have a very good idea that the largest samples of wind speed were actually taken around 1.2, 1.4 meters per second. So they had the largest number of samples of wind speed around 1.2 to 1.4 meters per second. Yeah. This shape that you see here in the histogram, you can then use a distribution to fit it. So in this particular case, the Weibull distribution is the distribution that most closely fits this sampling of the wind speed that you see here in the histogram. And because of that, they generally use Weibull distributions to define the wind speed of a specific site. So this is how distributions are derived, from using actual measured data in the field itself. Yeah? And in this case, with the wind being probably one of the most unpredictable and certainly most uncertain for renewable energy resources, the ability to now have this represented in some mathematical form is actually very useful, because we can use this in the calculations later on. So how is this used in the calculations? Well, what is normally done is you can take the wind speed, which you see on the top left corner here, which is Weibull distribution, and you can then take the power curve. So this is the meters per second wind speed and the actual output in per unit form of the turbine, and you can combine these two to get yourself a cumulative distribution of the actual output that can be expected from a wind turbine. And this distribution here is what you will then use in your calculations for your probabilistic analysis. Now this is for wind speed, so this obviously affects your generation. You can also use distribution estimation methods to look at, or deriving distributions from actual time series characteristics. Here's another example where the load of a customer is measured every hour of the year. So there's 8,760 measurements of this load. And what will happen is that you can use two methods. You can use a bootstrapping or histogram method, and you can convert this time series or time-based characteristic into a distribution. So the first method, bootstrapping, is again where they randomly it converts essentially this time series distribution into a cumulative distribution function. And what's very important to understand here is when the analysis is done, a random number is generated between 0 and 1. And that random number is then used to sample the actual value that will be used in the actual calculation itself. So you've taken this time series calculation and you've made it now into this distribution, and you can use this distribution in the calculations so that by randomly sampling, by taking random numbers between 0 and 1 and then getting a value to read off here in terms of the x-axis. So bootstrapping is one way of deriving a distribution. Another method is histogram. I did touch on this with the wind speed, but in this case here, exactly the same way, You define different bin sizes, so a load that will occur between a specific range. You then sample in this time series how many times you expected or that load occurred, and you count that up and you then tally up all the bins in here. And if you now look at this histogram and look at this time series calculation, you will see that the majority of the measurements were actually very low. So this particular load is running most of the time at a very low value. I also want to bring to your attention at this point where the deterministic methods fall short. If we were planning to supply this load, we would have looked at the maximum demand that this particular load will draw from the network. And you can see that's this one spike that occurred. It literally occurred only once in the year. And that spike over there, the probability of it occurring is so small, it's almost zero. Yeah? Whereas the majority of the time, the load is actually operating at a very, very low value. But the deterministic method would have given us an answer where we would have planned the network to supply for literally a single, an occurrence that occurred just once in the entire year. Yeah. So the probabilistic method is saying, yes, you can plan for that, but it's the likelihood of that occurring is very, very low. The probability of that occurring is a very low value. So maybe you're over planning your network. Maybe you should plan for more realistic values and then manage these sort of low probability values in a different manner by some active management of your power system. So that's just to give you an idea of how the deterministic and the probabilistic methods are starting to differ. Another thing that's always considered with probabilistic analysis is dependencies. So especially with generation, so PV plants in an area, if a cloud comes over an area, all the PV in a specific area will be affected. The same with wind. You know, the wind speed in a specific area is affected because the wind in an area is pretty much the same. Now, to take this into account in your analysis methods, what happens is you use what's called copulars. Okay, so copular means link or tie together. So you can link or tie together different types of generation sources. You can even tie together loads so that they all can give you a production or consumption in a specific area of operation. So as this also to let you know that modeling dependencies must also be taken into account. Now, once you've derived your distributions, it's really about running the analysis. And the analysis is done using what we call random number generation. So you generate a random number between 0 and 1. You then use your distribution to read off what the resulting load or generation value would be. And then you would obviously do your calculation based on that. And the more samples you take, the higher or the more results you get, which means that you will actually then start developing not a singular answer, but a multiple set of answers. So this is illustrated by the two graphs at the bottom here. You'll see there's random numbers that are generated, and you get a set of answers that fall within an area. Now, the two methods that I just want to touch on is one of the more popular used method is the Monte Carlo method. So it's really a broad class of computational algorithms that rely on repeated random number sampling to obtain a numerical result. Okay, so they just supply lots of random numbers and then they gather the results from there, and then the results are essentially processed later on using statistical methods. So I will show you that now. So normally you use some sort of random number generation method and you will process your results like normal load flows in your analysis. And once the results come out, that's where you use the statistics. Okay, so there's different types of statistical values that are used, but I think you'll see the value of this come back when I present the use cases to you. So where is probabilistic analysis used? Well, it can be used in different areas within power systems and power systems analysis. The first area that it's used is generation adequacy assessment. So you obviously need to assess the adequacy of the generation in order to meet supply. Okay, and we all know that the generation nowadays, especially with renewable generation, there's a high uncertainty that's introduced with renewables. Okay, so because of the uncertainty that comes with renewables, and as I mentioned, the uncertainty is actually coming from the fuel source, so the wind and the solar irradiation. Because of that, probabilistic analysis leads itself to doing generation adequacy assessments. Network planning, so obviously again, you have uncertainty in loads, uncertainty in embedded generation or distributed generation. It's naturally leading itself to using probabilistic methods. Short-term forecasting of networks. So this can also be, you can use probabilistic methods for this. Just to touch on this, in fact, short-term forecasting methods using probabilistic methods is used a lot in financial modeling. Whilst I was doing some of my research, I see there's quite a bit of financial models that use probabilistic methods. Network reliability, again, this uses probabilities to check how reliable a network is and how what's the occurrence or probability of something occurring. And then I also gonna hosting capacity assessment. Now, hosting capacity is I'll touch on it as an example, but you will see that there's a deterministic way of doing the calculation, or you could use a probabilistic way of doing a hosting capacity assessment. Yeah. So to get into, I'm going to give you two examples, very simple examples, network planning and on hosting capacity. So let me go there. So just to go back to how the planning is done. So obviously some sort of maximum demand and load growth is determined. So it's based on a load forecast. And the load forecasts are normally based on historical demand and forecasted trends and stuff. So you would have an area of study and you would say, okay, we expect the load to grow by X% based on the type of customer and the nature of the customer in that particular area. Right? Once you have these maximum demands, you might take some diversity into account, and then you would run your network, your load flow studies to check how the network will behave. So you would look for voltage constraints or loading constraints within the network. If there's distributed generation within this network, this can also be taken into account. However, because distributed generation can vary, you could end up with numerous cases if you were doing sampling and time characteristics. So what would normally happen is you would kind of define worst case scenarios, so these so-called extreme cases. For example, you could look at maximum load in an area and no generation, in which case can the network supply this, all the loads in the area. Then you would probably look at a case where you have low load in an area and maximum generation. But the real question comes is, what's the probability of these worst case scenarios actually occurring? Are we really planning for cases that hardly ever occur, or the probability of them occurring is very, very low? So to illustrate this, I have an example here where we have an MV network, and it has various embedded generation that's contained within the MV network. And the first way of planning this network was we looked at it in a very deterministic manner. So we got the maximum demands for all the loads. We populated all the loads with their maximum demands. We put in all the maximum or the installed capacity of all the generators in the system. And then we set up these so-called worst cases in the system. So the first case was the base case, where we pretty much put all the generators on and we put all the load on. And we found that when we did that, we had some overloading in the cables in area B. So the maximum cable overloading we recorded was about 94.5%. The next case we looked at was we increased all the load to the maximum, and we actually switched off all the generation. So all the generation is completely switched off. And in doing so, in this particular scenario, we found that the loading of the cables in area A became very high. So in that case there, we had cables loading at about 93%. So this was here in area A. And this particular case here of high load node generation, all the power was flowing into the area. We then swapped it around. We then made the loads in the entire network very low, and we increased the generation. So all generation was dispatched at its installed capacity or its maximum output. And we found that, again, the cables in area A was overloading. And in this case, particular case, we had overloading up to 106%. Now, if you are in network planning and if you are budget constrained, you need to decide, which area will get priority in terms of cable upgrades, because we don't have an infinite amount of money to upgrade our networks as and when. So the real question is, which of these two areas should get priority? Now, if you really look at it, cable A is supplying a large area. So there's a large area that's been supplied through those cables in A. Cable B has got two IPPs that are connected at the end here. And these IPPs have agreements. They have wheeling agreements that have to supply power into the system. So if you don't upgrade these cables and they fail, these IPPs, they won't be able to fulfill their wheeling agreements, and there could be serious contractual issues involved. So the question is, how do we determine which one gets priority? And what this comes down to is really trying to figure out which of these two areas, the cables, has the higher probability of overloading and failing. So to do this, we took the same network, but this time we did a probabilistic analysis. So the first thing we did was all these time-based characteristics, so all the measured characteristics for the customers that were in here, we converted them to distributions. The same with the generation resources. So the PV resources and the wind resources, we converted them into distributions. You then run a probabilistic analysis. So you run tens of thousands of samples where you generate random numbers between 0 and 1. And every time you do that, the tool will select a value for the load, or it will select a value for the generation. It will combine all of that into the model, and then it will run the load flow for that. So, and you run tens of thousands of these studies. Computationally, the methods have been improved dramatically, so that there is some computational overhead, but certainly modern computers are more than capable of handling this. And the results you get out now are not a singular value. You don't get a singular value. What you do is you get a range of values of loading based on different combinations of generation and different combinations of load. And when you look at the results, what you will find is, firstly, the same areas we identified before, area A has loading, there's overloading that occurs, but our estimation of the so-called worst cases that we made were actually not the worst cases. There are actually far worse cases that can occur between generation and load in the area that can result in loading up to 109, almost 110% of cables in area A. Second part is area B. Again, you'll see that area B loading was again also in the 100%. Yeah. Over and above area A and B, we also found that there were cables loaded above 90% in both area C and area D by looking at combinations of different load and generation in our probabilistic analysis. So the real question comes is, we have these cases where we've got these maximum loading. What's the probability of such a case occurring in reality? And this is where, for example, one of the factors we looked at was the empirical probability. So in area A, whilst we can get loading up to 110%, the probability of that occurring is very, very low. It's actually zero, almost zero. So it means this was just an extreme case that was generated by some combination of random numbers, but the chance of that occurring in reality is actually very low. On the other hand, if you looked at the loading of the cables in area B, here you would see there's a significant probability of overloading occurring in area B. And because of that, what this is saying is that if you had to upgrade between area A and area B, the chances are that the cables in area B, there's a higher probability of them overloading based and up to 102% based on all the tens of thousands of samples that we've taken. There's a very high probability that those cables will overload. So if you had to now determine where to invest in terms of cable upgrades, by looking at this set of results over here, you would see that maybe upgrading in the cables in area B might be a better return on investment because it is got the higher probability of overloading, and therefore by upgrading those cables you can reduce the risk that's actually imposed to the network. So this is a very simple example. Obviously you can go into great detail and analysis in terms of the mean values of loading and stuff like that, but I don't want to get too bogged down in the detail of evaluation. But to illustrate the concept that a probabilistic method can give us a slightly more definitive answer in terms of making our decisions as to how to plan this network. Another example I want to quickly touch on before I finish is hosting capacity. So hosting capacity is something that most distribution networks have to now start considering. And it's very simple because you have this huge influx of applications for people wanting to connect distributed generators or embedded generators in their systems. And the real question is, how much new generation can be connected to the grid without violating any constraints and without the need for expanding the network? So no network expansion required. How much additional generation can be taken into the network? Yeah. Now, the traditional deterministic method uses, you install the generator, you install some sort of load, and again the load is some predicted maximum demand or some value that you have in the system, and then you progressively increase the generation until such a time that a violation occurs. The violation could be a voltage violation or a thermal violation or loading or whatever. The other way of doing it is to use a probabilistic way. So what happens is you can introduce fictitious generation, and what's nice about this is you can introduce generation at only the points that are permissible to connect generation. So you can choose the points where you want to introduce the generators. You can then define distributions that are very specific to that particular area. Now, this is a very important point because remember, if you have PV and PV is installed in Durban, for example, the solar irradiation in Durban is completely different to if you were in, for example, the Northern Cape. Now, in Durban, you have a lot more cloud cover and the solar irradiation is not as strong as, for example, in the Northern Cape. So you find that the distributions for defining PV output in a PV plant installed in Durban would certainly be different from that installed in the Northern Cape, right? So you can define distributions very specific to that area. And then what you can do is you can run this probabilistic analysis, and you can look at the loading in the system. And you can monitor, for example, when an overloading occurs on specific lines in the system. And what you will see here is you get a range of results. So the top left graph illustrates a range of results. And if I chose a specific line, so here, for example, you see 100% is the cutoff. I'm saying I'm not going to go above 100% loading in the system. Then you would see that the 100% line runs across quite a few occurrences or cases that were set up from the probabilistic analysis. And now what you end up with is you don't end up with a singular value, but you end up with a range of values that explains to you, let me zoom in here, that you can actually expect the amount of embedded generation that you can actually take into the network is somewhere between just under 12,000 to just above 12,500. So it's a range of generation that you can take in terms of your hosting capacity in the network. The deterministic method would have given you a single value, whereas the probabilistic value gives you a range of values. And this is good because what it means is that you can then, if you have cases where people are applying and you're quite close to what is perceived to be a limit, or the limit determined by the deterministic method, and if you don't have the time to upgrade the system, a probabilistic analysis will give you a range that you can actually try and see if you can allow a bit more generation to be connected, that's within acceptable risk to your network. So this is just another way of using probabilistic methods, but in this case for hosting capacity analysis. So in summary, just to go back. So as I said, the modern electrical network is changing. It's under huge pressure to change in terms of allowing embedded generation and for consumers to now supply power back to the grid. And because of that, the conventional deterministic methods may actually result in over-planning and underutilized resources. So just, because of the uncertainty that's introduced by all this embedded generation, and even on the load side, there's an increased uncertainty in how loads are behaving nowadays. Probabilistic methods allow or allow for the uncertainty to be taken into account, and allows for the decision to be made based on a range of answers. So it's not a singular value, it's a range of answers, and it's really about managing or determining how much risk is acceptable. Now, it's all well and good having this, probabilistic methods, but I think we got to look at the way forward and how we as engineers and as members of the SAIEE can take our industry forward. I think this is very, very important. So certainly, if you look in the South African context, what we need to start developing is distributions. So data, the customer modeling data section of the flow chart. We need to start developing a library of distributions for customer types in South Africa. So the load customers, the typical customers with embedded generation, so the typical customers with just PV only. This is very, very important. So we must start developing this. And I think, there's a lot of data that's available. There's a huge amount of data that is actually out there in the system. What it is about some concerted effort to get it together and start processing it and developing this library of distributions, so that as we move into the future, we can start using this data in our analysis of the systems. And then the second part is to actually challenge the way things are done. So here, for example, you currently have network plans that are still done in a deterministic manner, but to challenge the results that come out of this by running some sample cases of probabilistic analysis and checking, are the deterministic results we get, are they still applicable? Or maybe we can manage the results or the outputs or manage the networks in a more active manner and not only do network upgrades. So yeah, it's about running probabilistic planning methods in parallel to the existing methods so that we can actually test the deterministic answers that we achieve. And yeah, with that being said, I want to thank you all for your attention. Our email is there, so if you have any questions or queries, please feel free to drop me an email. We'll try and answer it from there. Good. Thanks.
Thank you. Thank you, Jivan. Colleagues, then for the next part of this webinar, I'm going to hand over to my co-chair. His name is Marcus Dekkener. Marcus is a co-chair of the Load Research chapter. Thanks. Over to you, Marcus, to take the rest of the webinar. Thank you.
Sorry, Marcus, you're muted.
Mondi, thank you very much. Given, if you can show your face on the webcam, I appreciate that. Thank you. Okay, great, thanks. Given, very interesting talk, much appreciated. And we have a number of questions. I got a question here from Sven Moodley, who's asked, what about using real-time data for the network modeling? Do you have any comment on that?
Okay, so just to go back, so distributions are typically based on historical data. So you'll see that, for example, the measurement of wind speed or load profiles are typically done on historical performance. Real-time data is instantaneous, so this will give you a snapshot of what the network is like right now, but it may not be a representation of the full range of possible operation for the network itself. So I think real-time is good if you've got very short-term planning that you need to handle the network. So it's certainly used in that context, in short-term planning and operations of the network. But if you have to do plans, considering a longer-term basis, you need some sort of historical data to, the historical data must take the probability of something occurring into account. Therefore, measured data over a long period of time would be certainly more useful.
Yeah, I agree. But obviously, the question the point that's missing from his comment is that it's about catching the network doing something unusual, because it's those extremes that you're trying to accommodate as well. So much appreciated. You've essentially laid out almost a Monte Carlo simulation method here. And it struck me that it's almost a bit of a rabbit hole to a certain extent, because whilst you have a distribution over all time, you can also then go to different times of the day, perhaps, or seasons of the year, and run scenarios based on those. Have you got any comment there?
That actually is taken into account when you derive the distribution. So if you looked at that sample that I did for the load distribution estimation, that was for an entire year. So it took into account both summer and winter, and it was sampled at every hour in the day. Okay. So what it is that no 2 days are almost the same between customers, because obviously the consumption of a customer yesterday the profile is never going to overlap and be exactly the same as today. So because of that, the period you take the sample is very, very important. It's like anything. The more samples you take, the higher, what's not accuracy, but the more confidence you have. That's what I'm looking for. The more confidence you have in the sampling, and therefore you know the probability of that value occurring, as you can increase the probability of, or the more samples you get, increase the probability of that occurring. That's what I want to say.
Yeah, thanks. We have a question here from Ismail Khan. Does Power Factory automatically determine which PDF type to use, or is it user defined?
Okay, yeah, good question. You can, it's both. You can you can decide if you want, if you know what you want to use, you can define it, or by default Power Factory will take it for you. So
okay.
it will depend.
Thank you very much. Joshua Chayanduras asked if we can get a copy of the paper that you have written and presented based on this. Is that something which is available for later?
There is no paper on this, Marcus. Okay. I think the presentation is what we have as the source. I think the presentation will be shared. Confirm?
Yes, correct. That is correct. The presentation and the video will both be shared. Another question from Suvern Moodley is, most municipalities and substations throughout the country still have trouble with fault finding on their networks. This might not be a question, it might be more of a comment. Lack of foresight of what we do and what we have and what we do have and what we don't have regarding loads, such detailed links to maintenance as well. Okay, no, it's just a comment. At the moment, I don't have any further burning questions from the audience. My comment, though, that that struck me whilst you were talking was that whilst you are going through almost an algorithmic process, you said you do several thousand Monte Carlos. That can obviously, if you have business rules regarding your generation, for instance, and so on, there's potential there to incorporate those business rules into the Monte Carlo. Is there some kind of capacity that you know about to include that algorithmic side of things? In other words, the active network, and the active network busy doing its own dispatching, that kind of idea.
Yeah, so there's two ways of handling this. The one is obviously you can actually place active constraints on the generator itself. So if a generator has a physical constraint that's applied to it, you can put that constraint on there. So what it means is that even though the Monte Carlo simulation may say choose an output of 1 per unit, if there's a limit on that generator, the limit will then apply, meaning you will not exceed that limit. So the other way of looking at it is to say lift all limits from generators, and then what's the chance of that generator generating its maximum power, and that power flow into the system itself. And it's really a perspective thing, because from the network perspective, you wanna consider sort of all the different sort of cases where you can have maximum power flowing into the system, and how that will affect your system itself. So constraints can be taken into account. You certainly can do that. I did mention copulas. Copulas are very, very important because it also controls sort of that exact sort of thing, where you can limit the amount of export that comes from a group of generation in the area. Copulas can also be applied to load as well. So, a very simple example would be, assume you're doing a transmission type plan. If it's cold in the Cape, you would find all the load there would increase together versus if it was warm in Gauteng type of thing. So that can be certainly taken into account by use of active limits or constraints on the generation and copulas and stuff.
Yeah, certainly. What we've seen is that weather systems are great joiners of forces of behavior, rather, put it that way. It's very interesting in talking to the folks in municipalities about their concerns with PV systems and how the weather systems moving through impact on the simultaneous behavior of all the customers. Do you have any comments there? Have you seen anything like that?
Yes, certainly. So this goes back to what I was saying earlier about the way forward to determine a library of distributions for South Africa. Now, I think Suvan made a comment earlier, but it's important to note that data is the big input here. So getting data and putting it into the algorithm is the important bit here. And data is available on both sides. I know some of the Munichs have a lot of challenges with gathering data of their networks, but ironically, a lot of the customers have a huge amount of data that they have. For example, myself, I have a PV system. We have a PV system here in the office, and I have already months and months of data of how our PV system operates when it's cold, when it's raining, when it's windy. So this data is about getting it into one place that we can obviously store and then obviously process it from there. So yeah, it's just about getting the data into the system, Marcus, and then using that to push it through the analysis methods. And I do believe there's a lot of data. It's just about how do we share it in a manner that's useful for everybody.
Yes, I concur. That's a big challenge that we see on the load research side. Thanks. I'm out of questions at the moment on my side. If there's any further questions from the audience, please tap that into the question box. Mondi, do you have any further input from your side?
Yes, thanks, Marcus. No, thanks, Juven, for that very insightful presentation. So my question is a more rather very practical one, to say, if I'm the city of Cape Town, I see my colleague Ncedo Mkuzulwa is there, and now in planning he wants to adopt fully the probabilistic methods that you just presented. How much would that whole process, that changeover, how much would it cost in from the beginning to the end? Thanks.
Sure. I don't know how much it will cost, that's for sure. But I can tell you that the process of changeover is more a mindset shift. So it's about, it's not going to occur overnight. It has to be handled in a manner that builds confidence. And remember, one of the big things in evaluating the results from probabilistic calculations is how much risk is the actual municipality willing to absorb. Okay, so that's the first thing. And the second thing is, if we're not going to put some sort of network planning upgrade in place, how are we going to manage the occurrences of cases where at points you need to decide on the criteria, and that's the important bit. So each municipality may have different appetites or levels of risk, and that's the first thing that must be determined in the Munich as a whole. And the second thing is the actual methodology. How are we going to go about evaluating? What do we deem as acceptable, not acceptable? So the process is not an overnight thing. You can't just say, okay, we're going to stop doing deterministic, we're going to move to probabilistic. I think it's about building confidence. It's about taking small pieces of the network. And this was what I said with the way forward. If you have a plan, and if you have determined that these are the network upgrades that are going to be put into place, take the same plan for a small controlled area and push it through a probabilistic analysis. And in that way, you can learn what risk appetite you're willing to absorb and see how that would affect your final deterministic plan. In the little example I showed you, the question was really who to give the priority to upgrading, which cable gets priority for upgrading. That may not be the criteria for the municipality. There may be other criteria that they may need to use. So it's about developing that criteria as well. And then once you're happy with the criteria, you're happy with the risk, then you can start using the method, increasing the use of the method and using it more often. So I can't answer how much it's going to cost.
That's fine. I think that's good, that it does give an idea. And the last one, maybe from my side, Marcus, would be that on the very, very last slide that Jivan presented, I think there is some homework there that we have that in a way he has given to us now as load research chapter, that we now need to really start thinking about, how do we express all these variables probabilistically, and eventually, have the load classes or whatever we would call it being represented by the specific, distribution functions, just like he mentioned the wave wheel in terms of the wind, etc. So I think that is something we need to start pondering on and see if we can improve our standards going forward, and also the levels of risks. I think the way those notes in the last slide is probably something to start discussing further as a chapter. Thanks, Marcus.
Thank you, Mondi. And my last comment or question to you, Given, is what maximum demand is a parameter which is defined by risk. Have you, in your discussions, come across this issue about what maximum demand is in terms of a probabilistic definition? Because it's the highest load, therefore it should be the 100th percentile of load. But it's all about appetite for risk. So we go back to what is the definition of risk, and then you can decide on your appetite. Comments from yourself?
Yeah, look, On the maximum demand, it's also been based on trends. So they look at a typical customer class and they would say, okay, this customer class typically would consume X amount of power from the grid. And then using that as inputs, they like I said, and I did say the word, there's diversity that is applied to it. So they kind of take some of the, the risk is operated in a way of by using diversity. But at the end of the day, the aim of developing the maximum demand is to get some sort of value that's conservative in nature, so that when the plan is eventually determined, it can cover all cases. Do you understand? It's going to cover the all cases that can possibly exist. The real question probabilistic analysis asks is, all the cases that you're covering for, what's the probability of all of them occurring? Are you not over-designing the network? Yeah. And especially in the modern day, when we are so constrained by budgets, you want to make sure, you can save a lot of money by deferring upgrades to the network, so managing them actively, meaning maybe operationally you might need to manage them. So coming back to the maximum demand, it takes into account historical trends or consumer behavior, or certainly that's from a load perspective, and there is some sort of risk managed in it through diversity. But I think if you look at the probabilistic way of doing it, it's taking again the historical performance of a load or a generator, and it's using that to push it into the future and saying historically this is how it performed, and the chances are great that that's how it's going to perform in the future as well.
Yeah, great, thanks.
Marcus, there are two questions. The first one is from Wayne Kitching, who is part of the load research chapter. So what I think Wayne is making reference to non-wires solution, adding demand response DSM as a solution for those areas where you've got or where you've got high probability of occurrence, instead of putting a wires solution which could cost more. I don't know, Jivan, I think you did mention something to that effect.
Yeah, that's the active network management, Mondi. I did touch on that, and that's a valid point. Sometimes adding wire is not necessarily the most optimal solution to the problem.
Yes, certainly, you can manage the load away with an algorithm. Okay, let's move on to the question that we have from Zoe. Given's last answer prompts another question. Does our grid code allow us to consider risk probabilities rather than dictate deterministic capabilities? This is particularly relevant at a transmission level.
So I didn't get that, Marcus. Say that again, sorry.
Given's last answer prompts another question. Does our grid code allow us to consider risk probabilities rather than dictate deterministic capabilities? This is particularly relevant at a transmission level.
The grid code. Oh, I'm not sure. Maybe the planning grid code. I must look into that, Marcus. I got to look at the grid code, the planning code. But I know the planning code is traditionally based on a very deterministic type of approach. But
yes,
I would have to look at that.
I think Zoe's looking ahead.
Yeah.
All right.
I'm sure I can reply to that after this.
Yeah.
Thank you. Yes.
Marcus,
go ahead.
Marcus, if I can come in there, I think this is a very, very important question. In fact, I was expecting something to come from Zoe. If she said nothing, I was going to be disappointed. So this is one of those things that I think we need to look at, especially putting it either as part of the standard, because one of what I call a homework on the slide that Jivan had put was what level of risk can you accept? What can you deem acceptable? And Zoe is putting something here that's very practical. you accept a certain risk, and the situation that that 0.5% or whatever happens, then you, in terms of the grid code, you might find yourself on the wrong side of, you know, whatever the agreement is. So can we now start to, as part of adopting the whole probabilistic approach, can we start to put these things and say, this is now the level of risk that must be tolerated. If you are off for so much percent out of the year, then there is nothing wrong with that. It is in line with the grid code or with also the technical standards, etc. I think it is part of something that we need to look into, and as we move towards probabilistic analysis. Thanks.
Yes, thank you, Mondi. Any comment from yourself, Given?
No comment such. It's a valid point. I hear what Mondi is saying now.
Yes. Okay, folks, I think we're at the end of our time. I see it's 4:15. So from the load research chapter and from KwaZulu-Natal Center, I would like to thank you for sitting in and listening to the presentation by Given. And Given, you're much in demand, and we are very gratified to have you here to speak to us. And I hope that we will see more of you in the future. So thank you to yourself, and thank you to the audience for their participation. And thanks to Minx at the desk for SAIEE, much appreciated. Cheers then.
Thanks, Marcus. Thanks for the opportunity. Much appreciated as well.
Okay, then we will sign off now.